If you've ever written a piece of code, you know that nagging question that follows, is this actually any good? And when we say good, we usually mean efficient. But how do you actually measure that? I mean, do you just hit a stopwatch and hope for the best? Or is there a more scientific way to prove your approach is the right one? Well, that's exactly what we're going to break down. No, really, think about that for a second. How do you prove it? Is it good enough to just run the program and say, hey, it seems fast to me? Or is there a better, more rigorous way to know even before you've written a single line of code that your idea is solid? This is one of the core challenges in computer science. As it turns out, the answer isn't just one thing. To get the full picture of how well your code performs, you really need to look at it from two completely different angles. One happens in the world of theory and ideas, and the other happens in the real world, right there on the machine. And of course, these two approaches have their own fancy names: priori analysis and posteriori testing. So let's dive in and figure out what these terms actually mean, and more importantly, how they fit together when you're building software. Okay, first up is priori analysis. The key is right in the name. Priori means before. This is all the work you do on paper or on a whiteboard before any code gets written. You're looking at the algorithm's blueprint, its pure logic, to predict how it's going to behave and how its need for time and memory will grow. And on the other side, we have posteriori testing. You guessed it, posteriori means after. This is the hands-on part. You take the code you actually wrote, the finished program, and you run it on a real computer to collect cold, hard data on how it performed in a real environment. So you've got the on-paper theory versus the real-world practice. But what are the key differences? How do they really stack up? Let's put them side by side and do a direct comparison. The biggest, most fundamental difference is what you're actually analyzing. With priori analysis, you're focused on the abstract algorithm, the idea behind the code. But with posteriori testing, you're looking at the concrete program, the actual lines of code that have been compiled and are running. And that first difference leads directly to the next one, dependencies. Since priori analysis is purely theoretical, it's totally independent of any specific computer or programming language. It's a universal truth about the logic. Posteriori testing, it's the complete opposite. The results you get are entirely dependent on the machine you run it on. And when I say dependent, I mean really dependent. The results from a posteriori test can swing wildly based on your computer's CPU, the programming language you chose, your operating system, even what other programs you had running in the background. It's a snapshot of performance in one very specific context. And finally, let's talk about what you get out of each method. Priori analysis doesn't give you a hard number. It gives you a function, an approximation that describes how the performance will scale as your input gets bigger. Posteriori testing, on the other hand, gives you those exact numbers, like this took 20 milliseconds and used 5 megabytes of RAM. So a good way to think about it is like this. Priori gives you a general rule of thumb, like, hey, this algorithm's performance grows at a certain rate. Posteriori gives you a specific fact. On my laptop, with this exact data, it took 15 milliseconds. One is a broad principle, the other is a precise measurement. Now, it might sound like these two methods are fighting each other, but that's not it at all. In reality, they are a perfect team. They work together to take you all the way from the initial blueprint of an idea to a finished, tested, real-world solution. The smartest workflow uses both. See, you start with priori analysis. This lets you compare a bunch of different ideas on paper and pick the one that looks best before you waste a bunch of time coding. Then, you go ahead and implement that chosen algorithm. And finally, you use posteriori testing to make sure it actually works as well in the real world as you thought it would in theory. It really boils down to this simple idea. Theory guides your choice, and practice validates the result. You use your brain first to pick the right path, then you use the computer to prove you're right. So if you remember just one thing, let it be this. Priori analysis is all about the idea. Posteriori testing is all about the implementation. One is the blueprint, the other is the finished building. And I'll leave you with a little food for thought. What happens if an algorithm that's theoretically slower, based on your a priori analysis, actually runs faster in your real-world posteriori test? What does that tell you about your hardware, your programming language, or the specific data you're using? It's in that gap between theory and reality where things get really interesting. Thanks for watching.